seconds. Recording number VTC 6HT 82868. 20. Ten, 9, 8, 7, 6, 5, 4, 3.
This is the BBC television station at Alexandra Palace. At 3 o'clock this afternoon, the television service was opened by the Postmaster General using the Baird system. The opening program will now be repeated on the Marconi EMI system. The speeches are followed by the latest edition of the British Movietone News, then Adele Dixon and Buck and Bubbles, both accompanied by the television orchestra.
Well, that voice you just heard was the voice of the famous television and radio broadcaster Leslie Mitchell, and what he was announcing was the start of the world's first high-definition television service back in 1936. Well, I'm going to be talking about pictures through wires and through empty space, so I'm going to start by taking a photograph. I think I'll take one just about here. See if I can get you three boys in and perhaps something at the back. That looks nice. Nice smiles. Good. Splendid. By the way, we'll come to this fellow later. You may be able to just hear he's sort of rumbling away. We'll come back to him. But for the moment, I want you to have a look at this. Can any of you guess what it is? An old television. Yes, that's right. It was one of the very early television receivers before we started what I referred to as the high-definition service. I'll just tilt it back so that you can see this was the hole through which you looked, and behind it is a magnifying glass because the picture was very small, and it doesn't actually work now, so I can't show you this working. But what we have got is a recording that was taken from the transmission that worked this sort of receiver, an actual recording. So have a look at that. Now you hear this funny noise behind it. That was the sort of thing that happened, you see. There was a mechanical disc going round inside there, and you see there's just an image there of a face. It's wobbling up and down, and there are actually 30 vertical scanning lines, just 30 lines. Well, that's how television used to look like. Thank you. I think the wonderful thing is that that actually was recorded on a gramophone record, and that is the actual gramophone record. Well, it's taken 45 years for us to get back to the stage where we can actually put television on a disc, and I'll be coming to that in a later lecture. The reason, of course, is that that was very low definition television, and the bandwidth, this thing we keep talking about, was low enough for it to go on to an ordinary gramophone record. Well, I'm going to be talking about much wider bandwidths than that. How did it all start, this business? How did the ability to actually send pictures over wires start? Well, if you can take yourself back, first of all, 1827, now that's going back a long time, there was a metal called selenium discovered. I'm sorry, it was a non-metallic element called selenium, not a metal. And the interest was it was a new element. Nobody took a particular interest in it for a long time. It was interesting because it was a new element. But towards the end of the century, it started to be used as an electrical resistance. Now, you know, we talked about resistance. A high resistance doesn't pass very much current for a given voltage, and a low resistance passes a lot of current. So I want you to imagine that we're now in the year 1873, just 100 years ago, and telegraphy has started, and in Ireland there's a young man working on some telegraph apparatus at the terminal, and this is the sort of thing he'd be working on, coils and things like this, and he got a selenium resistance, and probably it was maybe it was late afternoon and the sun was coming into low angle, and he connected up his resistance like this, and then the sun passed across, and this is the sort of thing that happened. It suddenly made a noise, the meter started to flap around, and he realized that it was the sun's rays that were causing the trouble. Well, he didn't know why, so he took the problem to his boss, and his boss studied it, and he found out what was happening was that when the sunlight was shining on selenium, it lowered the resistance very dramatically, and that's what was causing the effect. Fine. So here was a substance that actually could respond to light. Now, we've talked about microphones responding to sound, and now we've got something that responds to light. So perhaps there's a promise here of being able to send pictures. So let's get hold of, imagine this is a piece of selenium, you see, and there it is. There's plenty of light falling on it, and I've got a large current. Put my hand over the end, and the current disappears. And as I vary the amount of light, so the current through it varies. So if I regard this as the equivalent of a microphone, then suppose we have a picture. I'll switch this on. There's a picture there. That's as bright as it'll go, yes. And regard this as the microphone. What does it make of it? Well, of course, it's not going to tell us really anything about the picture at all, because when you think of it, here is a still picture. Unlike a sound wave, which is varying in time, this isn't. The variations in light are occurring in space. So all this tells us is that it's a bright picture or it's a dim picture. That's all it would tell us. But if I bring the cell right up to the picture and start to examine areas of it, if I start here, I can see it's pretty dark. I run into the sky there and it gets light. I come along to the building, it gets a bit dark again, through the chimney pots, and along here, through the building, and on we go out into the light again, and so forth and so on. So if that picture was divided up into a lot of tiny little squares, it would be possible for me, using one of these things, to measure the light in each little square and send you a signal, and you would know how much light. And if you knew which square I was referring to, you could, by noting the meter readings, perhaps build up the picture. But that would be a very long way round of doing it, a tedious process. So instead, supposing you use the current directly that you receive, you amplify it and use it to light a lamp. Well, now here's one. And you see it's already decided to light because of the light that's falling on this cell. I'm going to just turn that down a little, so, and just see it should come up with a torch. It does indeed, you see. There we are. Now, supposing I use this in conjunction with my selenium cell on the end of this rod, and we start off here. I'll just make sure that it's just set up reasonably. You've got to set up all these things. Even today, you've got to do this sort of thing. Right. Now, if you imagine that this is looking at the sky, and now I'm running across the building, it goes darker, darker, bit lighter there, so forth, and so I'm back into the sky again. Now I'm reproducing the light. This end, this is the transmitting end, which is corresponding to the light of the image I was looking at. If in fact, this of course can be miles long, this cable, it was only a current that was going down, it could be a telephone wire. If that was a light which was passing across some photosensitive paper, sort of stuff we used to make prints out of, we could in fact record the light and reconstruct the photograph. And in fact, that was the way in which the early facsimile did work, not only the early ones in fact, but the later ones too. But I'm going to show you first of all a very early one. We'll just turn that off. This is one of the earliest pictures that were ever transmitted by facsimile. I wonder if you can just about make it out, perhaps, if we close. Have I got that upside down? Yes, I have. That way around. That's an aircraft, that's right. It's an old biplane. And actually, that picture was from an air display in Monte Carlo, and it was transmitted to Paris. You can just see these lines down here, very faint lines, and these were the lines that were caused as each successive part of the picture was scanned. What happened was they rolled the sensitive paper round a drum and revolved the drum, and then the light, the other end being received, varying as we just showed this one, was exposing the paper, so when it was developed, we got the picture. Well now, it may surprise you to learn that before we ever had television, still pictures were broadcast, and this was in the old days of sound radio. I'm grateful to a colleague of mine, Mr. Bernard Rogers, for lending me this piece of apparatus, because there aren't many of them around. It's quite historic. You use this in conjunction with your radio set, and I'm now talking of the year 1928, so we're going back a long time. And if you took the plug out of your loudspeaker and you plugged it in those terminals there, this valve amplified the signal. The signal passed through this wire, and it went into the box, ran up to this stylus here. And this time, it wasn't going to expose paper to light, but special paper that was treated chemically would get discolored when a current passed through it. It went purple, in fact, and later went brown. So in the same way that I mentioned you could wrap the thing round the drum, you wrapped your special paper round this drum, and then you wound it up just like you do a gramophone, or did rather. You don't have to do this these days, do you? And I'm going to operate this manually, but I want you to imagine that on the carrier wave, the sound wave, a little impulse was being sent out every so often, and doing what I'm going to do with my finger is just releasing a little clutch with a little electromagnetic coil, the sort of thing that we've talked a lot about, putting current through a coil, producing a magnet, and the magnet pulls this across, and watch what happens. Stop. Every time a pulse comes along, it does one revolution, stops, and this is on a screw here so that this is running along, tracing out a picture, just as the facsimile did. And that was actually broadcast, and it was in a piece of experimental apparatus that people could buy. It wasn't an experiment, by the way. It was never sort of a full service. Thank you. This is the picture, a picture that was actually received, and I think it's rather amusing. We've got, I think, Britannia here and John Bull there, and if you can read the word at the top here, she's holding up a disc, and it says picture transmission. Well, that was pretty good back in the days of 1928, wasn't it? We still use facsimile, and indeed, here, this thing that I was talking about is a modern one. This was loaned to us by Muirheads. I'm grateful to them. They make them, and they're used all over the world, and they're used by all the newspaper people, by Reuters, the news agencies, and indeed the BBC have a lot of them at Television Centre. We tried to borrow one of the BBC's, but they said they were far too busy there and used all the time, so we couldn't get hold of that. So we had to borrow one. And I'll just open the lid, and you won't be able to see a great deal, but it has got a drum It's got a lot of this photosensitive paper here, like paper used for printing. It's got enough to do over 300 prints. It's quite automatic. The paper is fed onto the drum. There's a light source which writes the picture onto the drum. And here are 2 tanks with chemicals in that do the developing. And the whole thing works unattended, chops off the pictures. And I see, in fact, we have a couple of pictures here that have arrived. No doubt that was why it was making the rumbling noise. Let's see what we've got. Yes, I think you'll be interested in that one and that one. Yes, I'll show you these. They're rather sort of still wet and sticky. You know, they're straight off the processing. So I'll put them in a little clip here. Try not to damage it. Now, I wonder if you recognize that. Wait till the camera comes up. Yes? That's you three. That's the photograph I took. Now you know why there was that rumbling noise going on. Well, that's that one. An actual photograph taken on the spot just a few moments ago. And this one is of the Radio Times front cover. And not today, no, January the 27th. Looks rather lively, doesn't it? This is January the 27th. It's the front cover, incidentally, has to be produced a long time before the Radio Times, so don't imagine everything's cut and dried as early as that. But those 2 have come through the machine. Well, that's fine, isn't it, for sending still pictures. But what do we do about moving pictures? Well, there was a man, yes, I'll come straight onto this now. There was a man called Carey in America that soon after the photocell had been developed, the selenium cell, thought of an idea. He thought, well, if I have a mosaic of these, a bank of these things, then each one could be connected to a separate source of light. Now we'll unveil this ceremoniously. Thank you, Bill. And I'll explain the apparatus. This was Carey's idea. He never built it, incidentally, but he thought of it. And it was very early on, as I say, only 2 years after the properties of selenium had been discovered. Now each one of these little holes here has behind it a photoelectric cell like the ones you've seen. And each one is connected to one of these lamps. Now, if we count along the row, there are only 10 along the top. There are 10 lamps. And there are 8 rows, 8 lamps down here. And each one is connected to the corresponding lamp. So there are only 80 possible picture points there. Now, if it's all working, and I switch it on and put some light on it, with a bit of luck, it ought to light up. And it does. Now we'll focus the light well onto it. Now this is quite a genuine thing. We are lighting these lamps by a light provided by this source onto these photocells. And watch when I put my hand across, you'll probably be able to see, there's my hand, there's my thumb, fingers. You can see that quite clearly. It's not bad, is it? It wouldn't make much of a picture, of course, but you see, if you could do that with enough lamps and enough cells, it would indeed make a picture. And indeed, it responds to the brightness of the light. Brighter, dimmer. So this Carey's idea was genuine television. Let's just try some. I'll leave it nice and bright and just try a couple of letters. You see, these are things with holes cut in, and they'll let the light through. What's that one? Oh, fine. Okay, good. And I wonder if you can guess what this is going to be. Yes, can you guess the next one? Yes. Okay, if it will fit in RI. You see, you could put simple messages over on a thing like that, but you wouldn't do very well putting pictures over. Now, there's a further difficulty, of course, was that if you really wanted these thousands of picture points that we're going to talk about, you would have to have thousands of wires, or you would have to have thousands of transmitters if you were going to do it through the ether. So Cary's thought was, and again, bearing in mind the date at which he thought of it, it was very bright. If we look at each one of these in turn separately, fast enough, we could perhaps switch and read them off from the top to the bottom. You would, of course, simultaneously having to be reading these off. I mean, this is the thing you're sending. You'd have to be reading off the current or voltage provided by the cells, running from the top line to the bottom. And have I had a little pencil torch somewhere? It doesn't really matter. If it's there, I think it's just worth showing because it gives the idea, I think, a little more vividly. We'll just put it on again. There we go. Instead of using that source, I'll just switch it on. And maybe there's too much light in the building. No, there isn't. Now, you see, I can actually run along there and run along there and so forth and so on. I won't bother to do that anymore because you've got a little model that will show it. So I'll switch this off and show what Cary's idea was. It's quite obvious, really, that you can get rid of all these wires and do it on just one wire if you treat each bulb at a time, and that's what this is going to do. It's only a demonstration piece to show the idea, but now if I turn this knob, I'm doing it a little fast there. Let's do it slowly. Work it up. There we go. Now you can see that quite clearly, starting at the top, reading down to the bottom. Of course, the one at the transmitting end would have to be exactly synchronized with the one at the receiving end so that you sent the right piece of information at the right time. Now, if I speed this up, the light will get dim simply because the light isn't there for a very long time. So it isn't going to illuminate the whole of the screen as it does nowadays with our modern cathode ray tubes. But that's the principle. Now, there were two things that we need to know. There are two things that we need to know before we can get an idea of how much information we have to transmit a moving picture. One is, how many of these little picture points do we want to make a good picture? And the other is, how often do we have to repeat the pictures? Because if they're going to be moving pictures, of course, the situation is different. With time, we've got to go on repeating the pictures. This, I'm sure you all know from the cinematograph. And in the early days, these, incidentally, were toys. I think this is rather fun, this. If you can just manage, if I tilt it over, we'll just manage perhaps to see through these slots. This thing, incidentally, was called a zoetrope, and it was a Victorian toy, virtually. Now, as I spin this, look at the monitors and see what happens. Can you see fairly clearly, I think, a succession of horses all galloping after each other? You can see their legs moving. Just do it once more. There we go. Well, that was before the cinematograph was invented, but it gave rise to it. Inside, you can see all there is a strip of paper with a succession of horses on, and each one is in a slightly different position. Its legs are moved with respect to the previous one, and we're looking through the slots. Thank you. Well, we know, actually, the answer to the first question from the cinematograph, but I think it's rather interesting to have a look. There are really two aspects to this. One is, if you're going to put pictures on one after the other, you may run into the problem of flicker, because unless the rate at which they're put on is fast, the eye will see the flickering. So for one reason, the pictures have got to be fast. And then there's a separate reason, of course, that if you want to portray movement nice and smoothly, you've got to take lots of pictures so that you take the action of the thing in a sufficient number of fixed positions to make it create the illusion of continuous motion. And I've got a film here that, before I show you the film, let's establish the flicker. You're quite right, yes. The flicker side of it can be established with, this is a stroboscope, It's a useful device and used scientifically quite a lot for other purposes. I'm just going to use it to create a flashing light. I'm going to start off with a fairly high frequency, and if it switches on, yes. Is that on? I'm trying to get the meter to read. Ah, that's right, yeah. Now, look, it isn't very bright. This is what you're supposed to be looking at. I'll move it as far as I can over towards it. It's the light on that sheet there. You will notice, incidentally, it's playing havoc with these monitors, and I'll come back to that in a minute. That's quite an important effect. But this light on the screen, I think you'd probably say was a fairly steady light, this light. Now, I'm going to turn the frequency down to the point where, quite obviously, you'll agree that it is, I'm sure, flickering now. If I come down to that speed. So I'm going to increase it, and when would you say that it's not flickering too badly, it's tolerable? Is that beginning to get all right? Not too bad? Somewhere around about there. Look, is it interesting? By the time we've got to there, do you see that bar going through the picture when you look at the monitors? Well, this is happening because this is switching on and off just at the same rate that those pictures are being presented to us. And the camera is just catching the thing. And when I say at the same rate, just at a slightly different rate, and that's why it's drifting through. And that is a very interesting effect, and this ability of the stroboscope to do this can be used to freeze things in motion. We're going to show you something I'm sure you've all seen before. Have you noticed how often it is that when you're looking at westerns, that the wagons that are going across the trail, the wheels go backwards? Well, I expect you all know why, but it's rather interesting just to demonstrate it live. I'll switch on again and see if we can catch the wheel and freeze it after Mr. Coates has spun it. Right. Now, there it is in steady. Make it go forwards or backwards, forwards. Now I've found the position, I'm going to ask Mr. Coates to spin it again, and we'll bring the lamp a little nearer and get it even brighter. That's steady, backwards, forwards. Well, that's quite a familiar effect, and there's another position where you can see we've actually doubled the number of spokes. Well, that's the price you pay for only looking at a thing every so often, but it's a rather valuable way of looking at machinery that's moving fast, and you want to be able to see what it's doing. Used quite a lot in science. The other one I mentioned, now that established, incidentally, that's that frequency that you were looking at, that you said, well, it was reasonable. It didn't flicker too badly. That was 50 cycles a second, 50 times a second the light was being flashed on. So we'll say that 50 times a second is all right for flicker. What about movement? Well, I have another film here which shows us pictures at different rates, but this time we've attended to the flicker. You're going to see pictures thrown on the screen 50 times a second, but as far as movement's concerned, it's already started. This is running at the normal speed, the stuff we're used to in the cinema, and you see there's an old organ grinder there winding his organ, and that looks perfectly normal. It's slow movement, there's no problem. Normal speed, quite good. It's gone into a fast sequence now where people are running, you see. That's Roger Bannister in front there, I think. And you see, even at that speed, the stuff we're used to, that rate is quite good. You can see the leg movement, not bad at all. A little bit of jerking perhaps at times as the camera moves very fast. The background may appear a bit jerky. And here's an express train coming in. That monitor seems to have a look at this one. This is better. Yes, it's got a fly. So that's all right, you see. Well, now we're going to repeat it, going back to the organ grinder again, but this time it's at 12.5 positions a second. And I think you'll see that it's rather a drastic change, of course, but I've done it purposely to just exaggerate it, you can see that it's tolerable. You can get all the information you need from that sort of picture. He's winding the organ, but it's jerky. Let's have a look at the runners. Well, now they're beginning to show a rather strange effect, aren't they? That's a bit of this stroboscopic effect we were saying. Their legs seem to just sort of be rather in two positions. Not impossible to look at, but rather unpleasant. And the express train coming in is coming in with a rather jerky motion. 12.5. Let's just, for the fun of it, take it right down to a lower speed still. We're going to show it now at 5 pictures a second. Now, 5 will be rather a joke, won't it? Look, it's a succession of stills. Even the old organ grinder begins to look quite comic. So we'll go over very soon to those runners and we'll see what they're doing. Well, the difficult thing is to believe that that is really 5 pictures a second, isn't it? It looks like 1, 2, 3, 4. You know, it's very slow. It's just catching their legs in that position. And we'll finally have a look at the express train. And I wouldn't like to be eating my soup while it's doing that. Well, the answer seems to be then an answer which we really... Thank you. The answer seems to be that we can put up with 25 pictures per second as far as movement is concerned, but we require 50 pictures as far as flicker is concerned. Now, in television, particularly, it's rather important that we don't have to send out pictures faster than we need to do, because I can assure you we're going to arrive at some rather alarming rates of information, and this uses up this precious thing we call bandwidth that we talked about, so we want to keep it as low as possible. In the cinema, they do quite a good trick. They also want, of course, conserve film. They do quite a useful trick so to satisfy the flicker rate and the movement rate. What happens is this. They don't, in fact, to be accurate, use 25 pictures a second as we do. They use 24. But each picture is thrown on the screen twice, simply by putting a shutter in front, so it interrupts it and then puts it on again. And then it moves on to the next frame, and that is shown twice again. Now, with 24 frames per second, which is enough for movement, near enough 25, you see, that gives us 48 for the flicker, which is good enough for flicker, especially viewed in dark conditions as we do in the cinema. At home, where there's some ambient lighting, actually, you're more conscious of flicker. You need to turn the brightness of the setup a bit more, so it's a good thing we're running a little bit higher than that. We're running at 50. How do you do it with television? You see, you can't put each picture on twice. You'd have to really store it somewhere and put it on twice, and it's not a very easy business. It isn't like just duplicating or just putting a shutter in front as it was with the film. Well, the way it's done is quite ingenious, and it's this. The argument is, supposing we've got any number you like of scanning lines, and we'll come to the number in a minute. Supposing we first of all scan with every other line. So if it was 100 lines, we only put up 50. And the next time round, in the next 50th of a second, we put in the other 50, but in between, interlaced as it's called. You can now imagine that although these lines aren't looking exactly in the same part of the picture, the two pictures are not going to be very different as far as the brightness is concerned. They're virtually the same pictures. So it is as if we had looked at the same picture twice. From the point of view of flicker, we're doing 25 frames per second, pictures per second, I should say, from the point of view of movement, but the flicker rate is 50, as near enough as it was for the film. So that is the way that the interlacing works and why it's rather important. Now, what about, that settled this first question I said, how many pictures do we require? We can get away with 25 per second. How many of those little things we call picture elements, in other words, if we were doing it with lamps, how many of those dots do we require? Well, let's have a look at this picture again. I think, yes, this one will do, of the one we took right at the beginning. And we'll just have a close-up look at that. I'm going over to this monitor here, and well, I can see detail here that you won't be able to see. If you were close enough, you could. But if I look, for example, at his spectacles there, closely, yes, very thin. There's some detail here. I can see this cloth here. Well, if I started to count up, you see, in about a centimetre of this picture, I would very soon be counting 10 changes from black to white. And if there are 30 centimetres across there, that would mean that we'd have to be thinking in terms of 30 changes from black to white, and that was from not very good detail. That was just from that picture. Some of the pictures are much sharper than that. And in fact, we find that we have to cater for something like 600 changes from black to white to get the sort of definition we require. And that really settles the number of scanning lines we require too, because the detail in the picture may be changing in the vertical direction or the horizontal. So in a square picture, if it was square, already I'm talking in terms of 600 in this direction, 600 in that, and if you multiply those two figures together, the total number of dots on the screen, can anyone do 600 times 600? 360,000, absolutely right, over 1/3 We're already up to that sort of figure, and we haven't even finished then because the picture is broader than it is high. We've got to add on some more for that. And then again, there's this very important business of having to keep the synchronizing right. We have to keep the, we have to send out an instruction so that this spot on the cathode ray tube is keeping pace with a spot on the camera tube. That has to be attended to too. Well, now I've been talking about picture tubes and camera tubes. I think just before I come back and show you anything further on this, I'll turn this down. What I'm going to do is just show you, thank you, one of the very early camera tubes, which was called an iconoscope. I'll just put it steadily down here so that maybe you can get a good look at it. I'll tilt it round, and you may be able to see, yes, I'm sure you can, there's a rectangular plate in the tube here, and that is really the equivalent of that little bank of photocells, only it's made up of a photosensitive chemical deposit, and it finishes up as little globules, tiny little ones, and each one of them represents a separate little photocell. They're not put on literally by hand in order, they're just formed on the plate, but you can regard it as being a lot of insulated little photocells, and each one of them is responding to the light that arrives through this window here from a lens system, and this is just like a photographic plate. That plate, the light comes through and is focused onto that plate. And now the little photoelectric cells, I should mention that we're not now talking about selenium. Selenium was the first discovery of a material that reacted to light, but since then materials have been discovered which, when you shine light on them, the light itself dislodges electrons, and we're back to this business that we've talked about so much before. Once you've got rid of, pulled away some electrons, you've got a charge there. So the plate has an electric charge over its surface. This is the full pattern of the image that's focused onto it, but now it's an electronic charge pattern. And what we want to do is to read off that charge pattern with a switching mechanism. And of course, it's got to be read off at this very high speed. The sort of speed you see we were talking about was going from the top to the bottom in a 25th of a second. We were talking about 600 lines. And if you start to work out 600 lines going from the top to the bottom in the 25th of a second, you'll find the spot has to go from one side to the other in about 66 microseconds. That's millionths of a second. So that's with modern television. In these days, it wasn't quite as fast as that, but these are the speeds we're talking about. So the only way you could do it, of course, was back to our electron beam, that useful device, that device that we use in the cathode ray tube, Now it's used at the other end. The beam is produced here in the same way that we've discussed before, focused onto the screen, discharges the elements, and a signal is produced, and that's how the old iconoscope works. Well, the new tubes don't work in a manner very different to that, excepting they're smaller and neater. This is the way everything goes, doesn't it? There's the picture focused onto the end, and this time we can use a semi-transparent material. The charge gets developed this side. Instead of having to look through at a queer angle, the beam can scan off on the other side. There it is. It's only 1 inch in diameter. I'm moving that about too much for you to see, but now you can probably see it. It's 1 inch in diameter, so long. Neat little tube. That's the modern tube. Just to come back then to these little sums I was doing, the sort of the amount of detail that we have to transmit, I got up to telling you that we were talking about scanning some 500,000 or so, getting on that way. If we do the sum accurately, it turns out to be about 440,000 little picture elements, and we want to scan all those 25 times a second. If you do the sum, we want to say something 11 million times a second. Now you remember when we were talking about sound and sound frequencies, the highest frequency we were saying that you need to transmit for good fidelity, for high fidelity, was about 15 kilohertz, and now we're talking about 11 million things we want to say. We don't have to use 11 million cycles to say this, because to oversimplify it, you can perhaps imagine that one of these cycles, the signal going up and down, one complete excursion of the signal up and down can say two things. It can say something about this part and something about that part. That's an oversimplification, but it does turn out that the actual bandwidth that you have to use to transmit 11 separate things per second is 5.5 megahertz, 5.5 million pieces of information per second. If that amount of information were to be transmitted on a teleprinter, and you know we saw a teleprinter earlier on, and if it were possible to make use of information at that rate, it's interesting to note that you could print the complete works of Shakespeare 3 times every second. Wouldn't be a very good program, would it? But that's the rate at which we're sending out information with television. Here are the synchronizing pulses that I talked about. I'll just turn the brightness up again, just to have a look. Now, at the moment, we're looking at the line synchronizing pulses. That is, the synchronizing pulses which are occurring here. I'll tell you what I'm going to do. I'm just going to unlock the picture so that it doesn't start at the right times. This may happen sometimes on your receiver, only not in such a steady fashion as this. I'd just like to be able to get a smooth picture that's just drifting through, if I can. It's rather critical, but it's a rather fine adjustment, but you can just see, I think, these black bands and those black bands. The picture isn't in the right place in either direction, and these are the synchronizing pulses. These are the pulses that are saying to the spot this end, okay, you can go in this direction, and when you get to the bottom, start up again at the top. So I'll put it back and make a decent picture of it. Oh, you can see them drifting by here, incidentally. Now, when I lock the picture, that's stationary, and we've come back to the normal position. If I could ask our cameraman just to pan the camera from side to side, you can just see, he can't do it very far, we'll lose this picture, but you can see the general movement here, just from side to side of the picture information. Unlike the sound waveform, which was bouncing up and down all the time, all very busy, this is relatively quiet, you see. It's just the information that is going along the lines, and unless something moves, very little moves in the picture. In fact, nothing, even if nothing's moving. And if I slow this speed down to this rate, now this is quite a slow rate, you can see these now lower frequency pulses. They are the field frequency pulses running at 50 a second. So there are synchronizing pulses. I didn't mention when I was mentioning the old iconoscope, it's only fair just to mention that when, in those days, in the very early days, that was the sort of receiver we had, but now, of course, you're used to these modern things much bigger. Now, remember when we were talking about sound, we had a look at the various effects you would get if you didn't take care of the signal. If you let, for example, the frequency response droop, if you lost high frequencies, lost low frequencies. Let's just do the same thing with television. And for this purpose, I've got a young lady who's going to come out and sit on this chair. Which is the young lady that said she would come and sit on the chair? Yes, that's right, you come. I just want you to sit on the chair, and the camera's going to be looking at you. That's right, lovely picture, marvelous. And what I'm going to do now is just to introduce some various effects. First of all, let's cut off the high frequencies and see what effect we get there. Sorry, there. Now, it isn't a very marked effect, but can you see the picture has gone what we would call soft? Now, we've cut off quite a lot. We've halved the bandwidth about, and it's a picture like that. Well, these nice pictures of a nice full face like this can get away with much less bandwidth, but generally speaking, the thing just looks out of focus. Now, when we did it with sound, it lost all its sharpness, it became woolly, we said. The picture becomes woolly too. What do you think will happen if I take away all the low frequencies? Can you imagine what the picture would look like? Could you make a guess? Horrible. Well, it certainly looked horrible. Or what's going to be left if I take away all the low frequencies? The high frequencies, and I'll have to turn the contrast up, and that's the effect. You see, all the high frequencies are doing is supplying information about things that the edges, as the scanning beam goes fast, the waveform moves very quickly. So you get this very plastic-looking effect. It's rather like something horrific out of Doctor Who, isn't it? With apologies to our young lady. Now, we can also, you remember we talked about noise. I think it's interesting to compare these effects because we've heard them on sound, and they're due to exactly the same cause, but, of course, being vision and not sound, the effects are different. Now, with sound, when we put on this random noise, we called it, this random fluctuation of electrons in the circuits that happened when the signal was very weak, then we heard it as a hiss. If we do it with television, we still call it noise. We haven't got a better name for it. And tell me what you think. I think it looks like noise, too. Some people actually refer to it as boiling porridge or snow, but formally we would call that a noisy picture. And indeed, I think all this speckled stuff does look like noise. That's what will happen, incidentally, if you try to receive a television picture with a very poor aerial system. You'll get a very weak signal, and so what you'll really be getting is all these little fluctuations that are produced inside the receiver because the signal you're receiving isn't strong enough. So that is random fluctuation noise. Back again to a normal picture. Again, we mentioned impulsive noise, didn't we? That was the sort of noise you get from sparks if you've got apparatus that isn't suppressed, if you have a motor car running outside your house and somebody's left it and they haven't suppressed it. This sort of effect, that's very annoying too. These are, you might say, unwanted ripples through the ether. Every time any of the apparatus we use produces a spark, it sends out one of these ripples. And that's what it looks like. Of course, on sound, we heard it as a click, 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 click noise. This is it on television. Let's go back again. Now, there's another one here. Do you remember on sound we listened to the effect of having another carrier signal that was too close? It was carrying some other information. It might have been just an unmodulated signal, just a plain carrier signal. It was too close to our own carrier, and it was producing a whistle. We had some ghastly whistling noises. Well, the equivalent on a television, of course, isn't a whistle. It must be a pattern, as you would expect. So I'm going to switch round and show you the effect of an interfering radio frequency carrier signal. And that is it, and you may have seen that sort of thing happening sometimes. If I creep down here without getting in your way, I can change the frequency of this, and you'll see various patterns that can occur according to how far the carrier is away from the carrier that we're interested in receiving. Now, that sort of thing can happen. That's quite an exaggerated case. But you remember when I was talking about the ionosphere, I said that the VHF frequencies and the UHF frequencies that we use for television in general don't get reflected from our ionosphere, particularly the UHF ones, but the VHF ones, and they're the ones not right up in the hundreds of megacycles, but round about the 40, 50, 60, I should say, megahertz. I still use this word that I've used for so many years. It's only recently, you see, they started calling them hertz and not cycles. These megahertz, these can get under abnormal weather conditions reflected from that lower layer I mentioned, the E layer, and we have what we call sporadic E. And in the summertime, in June, you can get signals, unwanted signals, from the continent due to this effect, and you do get those bars across the picture. Now, some of you may have seen those. You won't get them on UHF, but on the VHF service, you can still get them. So that's another sort of interference we've got to watch. Echoes. Now, I think this is quite an interesting thing, because this was what really gave, if I can find the, oh, there we are. I think it'll show up on our young lady here, I hope so. Get the plug in. Well, we're not seeing that very clearly. I'll try another one first and hope it comes good in the meantime. You know, we talked about putting too much into an amplifier, and it made nasty noises. It clipped off the top of the sound wave. The whole thing sounded very harsh and horrible. I'm going to ask our vision engineer if he would turn up the gain and overload the amplifier, and that's just what he's doing at the present time. Now, it's rather interesting. If you remember, in the case of sound, it produced a very, very unpleasant noise. This picture isn't a marvelous picture, but it's still recognizable. With television, you see, what's happened is that the top of the waveform and the bottom of the waveform have been clipped off, and so we've lost all the detail. Her face now looks as if it's absolutely plain white. You can see scarcely any detail in her jumper, and her hair here has just gone black. In fact, the whole thing is now either more or less black or white. It's gone between two limits. We call it sort of soot and whitewash. That's crushing. So that's the effect of distortion, which is quite different to the sort of thing we heard on sound. I'll just see if I can get this echo effect once more. Maybe, this looks better. Yes, indeed. I think it was my fault. I probably had a switch in the wrong position. Now, look, you may just be able to see here, I'm sure you will, that there's another double image. There's an image out here. Knowing the speed at which the spot is traveling across the screen, 66 microseconds about, taking time to get across the screen, I can measure that distance and say, oh, well, that distance of that second image is about 1 centimeter, say. I'm just doing this very roughly in round figures. If it's 30 centimeters across there, and that's 1, it's the 30th of the distance, well, let's just call it 60 and not 66 and divide by 30 into that, and we see that's 2 microseconds. And from that, and a knowledge of the velocity of light. Do you know what the velocity of light is? How fast it travels?
330 meters per second.
Very good, yes. I'm hearing 2 answers, and they're both right. 186,000 miles a second, or 300 million meters a second. Absolutely right. Well, from a knowledge of that, we can calculate how far the light's traveled in that time, and we could say how far the object was that was reflecting that second signal. And indeed, that was the birth of a radar. That's how it began to, that's how it started. Let me just now go on to, I think at this stage, I can relieve you. Thank you very much for sitting there and giving us such a charming picture. Thank you. One other interesting effect is the howl-round effect. On sound, you know, we saw yesterday that if we turned up the sound on the last lecture, I should have said, you've got a feedback effect and it howled. What happens if we do this to the camera? Well, if the camera looks at itself and it comes in, the camera is seeing the monitor, and on the monitor is a picture of the monitor. So therefore, on the picture of the monitor, there's another picture of another monitor, and you can go on like that, and you'll see this is the Hall of Mirrors. This is the typical effect, the Hall of Mirrors. Okay? Fine. Now, I think that's really shown us all the effects I wanted to show you, excepting one other, and that's the effect of moire interference, a moire pattern we call it. And to show you this, I expect you may have seen this sort of thing. If I take a pattern like this, this is a pattern which is coarse on the outside, and because all these radials get closer and closer together, it's fine on the inside. I'll take a similar one, and if I put it in front and manage to get it in reasonable register, well, you don't see very much, that's fine. But if I move it slightly, we start to get these marvelous patterns, and if I rotate it, you get all this sort of effect. And that's simply the different lines coming in and out of coincidence causing that effect. It's called moire because moire silk shows this effect. It's rather attractive, but it's not very attractive on television. And now I'm going to ask a boy here who's got a tie on with a fine pattern on, just to sit on the chair for us. And if we take this at the right distance, we'll probably be able to produce an effect which is not a very nice effect. Unfortunately, it does happen at times. It's one of the prices one has to pay for having a finite number of scanning lines. Perhaps if we unbutton your coat and let's see more of your tie, we may get it down the tie. We just come in, it's a critical point, and you may, there we are. You see those stripes that are appearing there? Yeah, they are, just like those stripes we're looking at on the pattern. Well, you sometimes see that on television. That's another little defect we get. But on the whole, I think it all works pretty well. But there is one snag. Of course, what we've been looking at is only in black and white. And on many occasions, color can be very important. We have, for example, traffic lights. You drive and you know the position of the traffic lights according to the color. I may ask you, yes, thank you very much indeed. I don't want you to sit here any longer, I'm sorry. Thank you. I may ask you to meet somebody at the station. You say, well, how will I recognize them? And you say, well, they're wearing a red carnation. Animals, of course, use color a great deal. It's very important in nature, and what we've been looking at the moment has given us the shape of things quite well, but not the color. In my next lecture, I'll be discussing how it's possible to send information of color along wires and through empty space. Thank you.
Could I just keep you for one more second? I wonder how many of you read the papers this morning?